Hello. So last time we defined the type of dependent pairs, and now I wish to use what we've built to do a bit of algebra. So we'll talk about the Eckmann-Hilton argument, uh, which is a statement about unital magmas having two multiplication on them. So the reason why I'm doing this now and why dependent pairs are interesting is because the whole idea when you define a structure in algebra is you have a set and then you put a structure on it. And usually the structure is given by multiplication, right? But here we don't really have sets, we have types. So we are going to put a structure on a type. Therefore, if we want to bundle, like have one object talking about, like, say, a group or a magma or a monoid or anything like that, we want to bundle data together. We need to first give the carrier set, which is going to be, or the carrier type, sorry, which is going to be the underlying type of the algebraic object. And let's say this carrier type is called alpha. It's called alpha. Then the multiplication that we want to impose on this alpha is going to have some type like this, right? So it's going to be a binary operation. It's going to be a binary operation on this type. So the domain is Cartesian product, and the codomain is just alpha. Here it's going to be easier if we just write this in the equivalent way. So m still takes two arguments. It's simpler to write like that. You'll see. So as you can see here, the type of the multiplication, it depends on the actual value of the carrier type. So if we have carrier type alpha, then the multiplication will have type alpha, alpha, alpha. And if we use a different carrier type, beta, then the multiplication will have a different type. So it gets even worse because we want to define unital magmas. So what are those? So unital magmas. We have a carrier type. We have a binary operation, and there's no magma means there is no constraint. Like, it's possible this operation isn't even associative. But what we have is a unit. There is a special element, like we pinpoint one element u or unit, and this is going to verify the following. So we want that multiplying by the unit does nothing, right? As one would expect. So if you write it functionally, we have the left unit law. So let's say for all x, we want to have mux. No, sorry, this is the left unit. We want this. This is going to be left unit. And you want the same thing, but on the other side. Like that. And as you can see, the type of this thing here, it depends both on m, and it depends also on what the value of u is, because this is a type, right? And we're asking for proof of this type. So the ideal tool, or the first tool that comes to mind, and really it's the right tool for the job, is dependent pairs. Let's formalize this little green comment here. So we'll start with the definition. Sorry, I have my notes here. So the first thing that we would like is to define the type of all unital magmas. Okay, so, and the idea here is that given the term of this type, we will know that it represents, or it bundles up all the data needed to describe a unital magma. So it will have the carrier type, it will have the multiplication, it will have the unit, and it will have proofs that the unit is like left identity, right identity. So we want to define it like something like that, right? The first argument to the pair is the carrier type. right? And the type of the carrier type is type, so this is what we put here. And now the type of the second argument, well, remember it can be it can depend on the value of the first component, which is going to be called here alpha, and then we must build a new type. And this is where the unital structure goes. Unital, all right, str because it's the structure, and then just alpha. We haven't defined this yet, so you know, Lean it doesn't know what to do. It's like, what the hell? Here, this is a function that simply applies alpha to another function, so this is basically the same thing as just like that. Okay. Now to define the actual structure. So magma. Okay, so this is going to be a function that takes some type as a parameter and produces the type as output. So if we just sorry that, we can see the error here, it goes away, and here there's a warning. We need to actually define this. So we want to bundle. Right now we have bundled this, it's here, and we need to bundle all of this. So the first argument to the pair should be this type right here. Let's just copy paste this. This type, like, so we will have a pair, and the first component will be the multiplication, which has this type here. And the second component is allowed to depend on what this multiplication m is. So here we want a type that represents this. So it's going to be another dependent pair. And the first component of that new pair is going to be the unit, like a choice of unit. So we want the type to be alpha. And now the second component of this inner pair is going to be allowed to depend on what the choice of unit is. Okay, and inside here we want these two proofs. So I'll just write them. It's going to be something and something else. Okay, laziness take over. Oops. Yeah, okay, so you see we have the left unit, right unit. We'll call this not left unit, but we will call this U mole. Because if this M was in the center here, like a binary operation, you would have the U to the left. And for the same reason, we will call this one mole U. Okay, perfect. So we have the definition of unital magma structure. Let's put ourselves in a namespace. Namespace. That's funny. Unital magma structure. Okay. So the first function that will be kind of useful if you want to build some kind of API using the structure is going to be constructor, some kind of ad hoc constructor that is able to just easily create a value of type magma, unital magma. You know, we could do it the long way, but this constructor will allow us to do it in a shorter way. So, you know, we say that given this multiplication, well, given some multiplication, notice here that I wrote alpha without declaring it in the local context. So Lean helpfully puts it as an implicit argument here. but I could achieve the same result by just doing it myself. I could say alpha is a type, and the curly brackets, like I said last time, it's an implicit argument. And yeah, maybe I should say the reason why we can put an implicit argument here and everything will work like as we expected is because Lean can check like, oh, what's the type of M at the call site of MK? You know, when we actually use MK, Lean will look at, oh, what's the type of M? And it sees inside the type there's alpha. So it knows how to, from the type of M, it knows what the type alpha should be because it's written in the type of M. Okay, so in some sense, every bookkeeping argument, we can usually put them in implicit, in these curly brackets, which mean implicit arguments. So we have given a choice of multiplication, given a choice of units, and also given proofs that this is a unit. Okay, laziness take over. So given a choice of multiplication, a choice of unit, and proofs, two proofs that this is really a unit, we can produce a value of type unital magma structure on the type alpha, right? And this is just calling the MK constructor in a user-friendly way, let's say. Okay, so this is just API stuff. Usually we wouldn't have to do this. Like, you wouldn't, like, there are some special syntactic constructs that Lean uses, like people use when they write code in Lean to write dependent pairs in a different way than what we've done. I'm just doing this for learning purposes. Usually we would use the structure keyword and we wouldn't have to make this, like write this constructor ourselves. It would be generated automatically by Lean. And similarly, we can define more boilerplate, which I'm just going to copy paste from my notes. And this is just to be able to write, like, given a structure, I want to be able to write just structure.m. I don't want to have to write like proj1 and stuff like that. But like I said, usually Lean will do that for us. This is just because we're doing it the hard way, if you will, just for learning purposes. We can already prove some stuff. You know, we can prove, for instance, a really easy theorem that says this. It says this. So given any structure of a unital magma on alpha, then for any x, the multiplication induced by this structure or afforded by this structure will commute with the unit. So this is really simple. Here, this is the way we talk about the multiplication of the given structure. So the unit of the structure multiplied by any element is going to be equal to this. Yeah, so this is just saying the unit commutes with multiplication, which is really, like, mathematically it's trivial, but how do we prove that in Lean? Well, we want to prove this. So remember last time, you know, when you have a for all, what you do is intro, and we give this a name, let's say x. Notice if I don't give it a name, it's going to put a name by itself, it's going to call it like X with this dagger here. And this dagger means that it's an inaccessible name, like we can't talk about it, even though Lean can see it. But we want to give it the name. And then we need to prove this. But this is not too hard. We can use a new command that I haven't talked about yet. This is called the rewrite command. It's written like that, and it allows you to rewrite something using a proof of equality. For instance, here we know that this, by the proof u left, we know that this is equal to x. There's a proof of that. There's a proof that mux is equal to x. This is u mole. So I'm just going to write that. Oops. Why is it not working? Oh, that's because here I called it u left. This is not what I want. This is, I want to call this u mole. Oops. Little copy paste error here. And this is mole u. So if we come back here, we can see in the info view, Lean will helpfully highlight in red what it's going to rewrite. So if I just step the cursor one character to the right, we can see it just rewrites this to x. And we will do the same thing with this part here. And using mol u, we will rewrite this to be just x. There we go. And there's no more goals because we changed the goal to something trivial. Like to prove this, yet again, you can use reflexivity of equality, and Lean is smart enough to just do it by itself. So, yay! Goals accomplished. That's nice. Anyways, this was quite easy. Now let's go to the Eckmann-Hilton argument. We have enough, well, almost enough formalized to be able to do it. The only little thing that we need is like the Eckmann-Hilton argument talks about a compatibility condition. It talks about two different structures on a unital magma. And it says that under the condition that these structures are compatible in some sense, then we have some nice things that are happening. So it's going to be easier if we just put in writing what this compatibility condition is. I'm just going to copy paste it. Laziness take over. Okay, this is the condition in question, the compatibility condition. So it says that given structure 1 and structure 2, which are two unital magma structures, we can express the compatibility condition as follows. Like this means that structure 1 and structure 2 are compatible. Basically, you may multiply A and B using the multiplication of the second structure, and you also may multiply C and D. And these two new elements, you can multiply them using the multiplication in the first structure, right? So you can do that, and you can do the same idea, the same thing, but instead of starting with the first structure, instead of starting with the second structure inside here, you rather start with the first structure. So there's like some kind of twisting going on. And there's a nice way to see that, to like picture it. So you can say, for instance, that the first structure, it is vertical. You'll see what I mean. So the first structure is vertical and the second is horizontal. Still getting used to that keyboard, yeah. So we say the first structure is vertical and the second is horizontal, and what I mean is, I mean like how we write multiplication. So if we multiply using the second structure and we multiply together A and B, we will write it horizontally like this. And if we multiply using the first structure, we will write it we'll write it horizontally. Oops, like that. Okay, so there's two ways to write multiplication. And then what the compat condition says it says that if you begin with multiplying horizontally, so AB, so if you begin by multiplying horizontally here and here, and then you do vertical multiplication, this is the same as where are my, okay, this is going to be tricky doing live ASCII art. Okay. This is going to be the same as first doing the vertical multiplication here, as you can see, AC, AC, and BD, BD. So first doing this and then doing the horizontal multiplication. So this is what the compatibility condition says. It says basically that it is unambiguous unambiguous to when you write some kind of matrix of elements like that, it is unambiguous to just write it as ABC. You don't need parentheses to specify like which multiplication you do first, the horizontal or the vertical one. So this is like the intuition behind the compatibility condition. Okay. So the first theorem that is interesting for us to prove about some structures, so about a pair of structures, let's say. I'll write it like that. One is that if you have structure 1, structure 2, then on the same base type, right? Then their units are actually the same. So this is what we want to prove. So let's say we have two structures that I will give them as implicit arguments to this theorem here. And suppose that we know these structures are compatible. Then the unit of the first structure is going to be equal to the unit of the second structure. And we will do this proof using tactic mode. So what is the goal here? Lean recognizes that the goal is to show the units are the same. This is going to be simply rewriting stuff, nothing too complicated. So the first thing here, notice you would like to use, we don't have much to our disposition, we would like to use the fact that U is a left unit first. So we can rewrite stuff using rewrite, right? Let's say umol. And if we look at the form of this umol here, okay, this is the form. it's like we have this, we have the simple thing, and we want the more complicated thing. So usually we'll rewrite stuff from left to right. So it would see something of this form and replace it with X. We want to go the other direction, so we need to use this arrow here. But the only problem is, we don't have enough information right now, so we need to give it more. What do we want to rewrite? This is the unit of the first structure. I'm not sure. Oh, yeah. Yeah. Okay. So the problem here is the first argument to UMO is actually the structure in question. We could probably just put that as an implicit argument, because I think Lean is able to figure out by itself what the structure should be. Yeah, so that works. Nice. Whoa. Oh, what is this? Okay, these are meta variables, and yeah, when they appear like that, it's usually bad news. That's because Lean is not able to figure out actually what the structure is. We have two goals now, and Lean is like, okay, so I can rewrite this for you, but you need to tell me like tell me what the structure is, please. Okay, so we won't put implicit arguments here. We'll just like do Lean's job for him. Okay, and now you see we had this, which is highlighted in red. Thank you, Lean, very helpful. And then it becomes this. Basically, this is u times u, as you can see. This is u times u. Okay, perfect. We want to rewrite even more because we want to use the compatibility condition, right? So we can see that if here this was written using multiplication, and if here this was written using multiplication, both of those in the second structure, then we would be able to use our hypothesis. Okay, so we may rewrite yet again, same idea. We want to transform this second parameter here. We want to write this as the second multiplication of the second unit times the first unit. So the way to do that is using a rewrite call yet again, and this time using the second structure, and still using the unit of the first structure. The only problem here, as you can see, is that it would Lean detects that there's two things that match our description here. There's two things that will be replaced, but that's not what we want. We want to replace only the first thing. So the helpful thing to know is that each command in tactic mode may take some arguments. Here we want to rewrite only the first occurrence. So there is a parameter for that, and there's some kind of syntax for it, but this is just saying that, okay, we want to replace only the first occurrence, and see, this is what's happening here. So everything's good. Now we replace the second parameter, so this is going to be the second occurrence of this little thing here, and instead of using umul, we'll use mul. Recall, because this is in order for this left hand term to be compatible with the, well, to use a compatibility condition. So let's use it. Compat. Oops. Okay. If we look here at the info view, we see what will change. So if I step the cursor one character to the right, we see that there is some kind of permutation going on. This is the effect of the compatibility condition. So here you see it's changing from the from the first multiplication into the second multiplication, and you know the opposite thing is happening here and here. So now we want to we made the left hand side grow up. Now we want to shrink it down. So we know that if we can use the first structure, it's oops, volume. No, and we see this is because you know, the first multiplication using the first unit, it does nothing. So this is what's happening here. It just replaced this whole thing with the unit of the second structure. Yeah, and we will do the same thing here. This is supposed to be the left unit condition for the first multiplication. So like that. Okay, everything's looking good, and then finally we have this thing here, which is obviously equal to this because U is a unit for the second structure. So for this one, we may use either left or the right unit condition. Here I'm going to use this. And finally, the goal is to prove something is equal to itself, and this is trivial using reflexivity of equality, which Lean is smart enough to do by itself. So goal accomplished. Excellent. Okay, so we've shown that given two structures on a unital magma, if these structures are compatible, then they define actually the same unit. So they must have the same unit. Okay. Now the actual Eckmann-Hilton argument says that not only are the units the same, but actually the whole multiplications are the same. So the compatibility condition is enough to guarantee that your two structures are actually the same structure, and moreover, it is enough to guarantee that this multiplication, either one of them because they are equal, is so it's enough to ensure that the multiplication is commutative. So just because I'm running out of time, we will prove only the commutativity of, let's say, the first multiplication. But, you know, this is an exercise for the listener. You can try to formalize the rest of the arguments at home or something. So for this, we need two structures. Two structures over the same magma alpha. And we also need that these structures are compatible. Okay. And this will be enough to guarantee that the first multiplication is commutative, or the second, they are equal, but you know, let's just choose the first one. So let's write it like that. Yeah. We will prove this using tactic mode, of course. Okay, so let's see here. We have intro. We have a for all, so let's introduce our variables into the local context here. And now this is what we want to show. So how to do this? This is maybe not that interesting, but it's just like an exercise in rewriting stuff, you know. So we will rewrite this expression until it's trivial. Basically, that's the idea here. So we recall what we have at our disposal here is the compatibility condition. So we want to massage this expression until we can use it. That's basically the only thing we can do. And the only way we can massage this expression is using the left and right unit laws we have. Let's use the left one to change this x here into multiplication of x with the unit in the second structure. This makes sense. Yeah, that should work. Oops, like that. Okay, and we want to rewrite only the first one. This is the same problem that we had earlier, so I'll just copy paste this, laziness take over, and now, okay, this is cool, this is working. We will change the second argument here, this one precisely, into this y multiplied by the unit in the second structure again. So I'll just copy paste this, and we still want only the first occurrence of y, and we want to multiply on the right. We want to multiply by the unit on the right. So the expression is now this, which is completely equivalent to what we started with. Which if you do the argument on paper, you see this is you won't even think about like justifying these steps, but here we need to do it. Now we can use the compatibility condition, which was the first goal, and what happened is there is some kind of permutation going on. So every instance of the first structure becomes an instance of the second and vice versa. And also this x becomes a y and this y becomes an x. Cool. Now we see here it's interesting because we have that multiplication in the first structure of the second unit. But we know that the second unit is actually equal to the first unit. So this here should be equal to just y. We need to use what we proved earlier. Right? We need to use this. And we will use what we've proved to replace the second unit with the first unit. So if we look at the statement here, we see we can do that, but it's just we're going to need to go from left to right. So I'll just put the little arrow here and write Eckmann-Hilton and give it the appropriate parameters, or maybe I don't need to. Yeah, looks like it's able to find it by itself. Nice. Wait, what? Oh no, I'm using the wrong thing. This is what we want. And yeah, we need to give it the compat condition, I guess. Yeah, so you see here, it replaces these instances of the second unit with the first unit. And this is perfect for us because now when we do this multiplication, this does nothing by the left unit law, and this by the right unit law does nothing. So you will write this here, this, and this. And what happened to the expression? We made some progress, right? So the order here is fine, but here we have the multiplication in the second structure, while here it's in the first one. So this is not exactly what we want, but we made some progress. Now we can do some more rewriting. You know, it never stops really. But usually, when we will have more tools at our disposal, this is not going to be so painful to do. Usually also you this kind of proof, it's better to just do it on paper first, and then when you're ready, you can formalize it, and it's basically quite easy. But maybe don't try to understand all the argument. It's quite simple. It's just try to focus on the lean part of it. So we will rewrite this part here. Okay. And yeah, we want, like, this is the correct thing here, but we want only the first occurrence to be replaced. So I'll just put that here. This is nice, and yeah, we'll do the same thing again. Yeah, this should work. So if we look at the difference here, we had str2.myx, and now we have just multiplied the argument by the unit, so nothing is happening. But we are actually almost done, because we can just rewrite using the compatibility condition. First off, this has the effect of changing this 2 for 1, which is good, because if we look at the right hand side, we see there's a 1 here, so we need to change it for 1. And now we know the units are the same, right? We like this here. If we had the second unit here, we could like apply theorems. So we'll just we know that the units are the same actually. So that, and now we use multiplication on like identity of the multiplication by unit. That, and same thing. Oh, shoot. Sorry. So this should be like that. Yeah, this makes way more sense. Yeah. Sorry, guys. So this should be y times this. Yeah. And then we're done. Yeah, great. Because we see we succeeded in changing this, like, in having something that can be trivially proven. All right. So this is what I wanted to talk about today. Do a little bit of algebra, formalize some easy arguments. It's not like the most interesting argument to formalize, because it's really simple just on paper. So you wouldn't really need to do that or anything like that. It's just to show how we can use what we've built when doing dependent pairs, and how it can be used to do algebra and in this kind of system. Usually people, when we write lean code, we won't like define dependent pairs like that. There's a keyword called structure that will give you this idea of having dependent pairs, but also many goodies and automatically generated stuff that can be really useful. Like, for instance, here we shouldn't have to define these. These are really basic boilerplate stuff that can be automatically generated, and usually lean is able to do it. Same thing for the constructor here. It's like we just use this to make it easier for us to use our type. But when we define, if we would define a unital magma using the structure keyword, then this constructor would be free, and we wouldn't have to actually define it. It would, like, this can be mechanically generated, of course. I hope this was interesting. Next time I want to talk about another inductive type. I want to talk about the most well-known inductive type. I want to talk about the natural numbers and how we can define them inside of lean, and then possibly prove some easy stuff about them. I want to proved the fundamental theorem of arithmetic, which says that any positive natural number may be written as a product of prime in a unique way. But I think that this is going to make for a way too long video, so I'm not sure yet. But I do want to talk about the natural numbers, and I do want to talk about how the recursor in this case corresponds to like induction and definitions by recursion as we are used to in maths. So I hope to see you next time and have a nice day.